So hello, we're on to series lecture 11, the integral test. Actually, this is the third time I've done this. Something keeps going wrong with it. So let's see if it uploads correctly this time. So the integral test is going to be the first test we have to test whether a generic series converges or diverges. So we're going to be looking at the series sum of k equals 1 to infinity of ak, where ak is equal to f of k, where f of x is some decreasing positive continuous functions defined on the half line from 1 to infinity. So we're looking at the series. Let's make that a nicer color, the series k equals 1 to infinity of ak, right? And we are going to understand whether or not that converges by looking at the integral. So I'm going to put something down here. First off, I'm going to look at these little rectangles here. Now what I've got here in red are the points 1, A1, 2, A2, right? F of 1 is A1, F of 2 is A2. So those are, I've marked off the terms of the series as points on this line. And I'm going to draw these little rectangles here. So on down the road. So what do I know about those little rectangles? Well, I can figure out the areas of those little rectangles, right? I can say the area of this first one, well, the width is 1, and the height is what? It's A2, right? So the area of that first rectangle is A2. The area of the second rectangle, the width is 1, the height is A3. The area of the third rectangle, again, A4, 1 times A4, and so on down the road. So if I were to add up all of those, the areas of all of those little rectangles, I would end up with the sum k equals 2 to infinity of ak. But if you notice, that's going to be less than or equal to, in fact, less than the sum, the integral from 1 to infinity of f of x dx, right? Because it's completely below the function f of x. So that area is going to be part of, but not the whole part of, the area under the graph of f of x. So in other words, if f of x, if that integral converges, if this integral right here converges, goes to something finite, that means the sum has to converge as well, right? Well, if the sum k equals 2 to infinity and converges, the sum k equals 1 to infinity also converges, because that's just adding one extra term onto it. So in other words, if the integral converges, then the series converges. Now I'm going to look at some other rectangles over here. So let's look at something a little bit different now. I'm going to take from going up this way and over. And again, I have exactly the same graph here. So each of these red dots are at 1, A1, 2, A2, 3, A3, and so on down the road. So it's exactly the same graph, but I'm just looking at different rectangles here. Sorry, my rectangles aren't too rectangly. So let's look at these rectangles instead. So here we've got the left endpoint coming up to the graph. And if I look at those rectangles, well, again, we can find the areas of those. This is the widths of each of them is 1. The height of the first one is A1, so 1 times A1 is that area. The height of the second one is A2. Height of the third one's A3, and so on down the road. So the sum of those little rectangles is going to be the series k equals 1 to infinity of ak. And as you can see, that's bigger than or equal to the integral from 1 to infinity of f of x dx. So in other words, if the integral diverges, meaning goes off to infinity, these rectangles, I mean the series must also diverge. So that first picture says if the integral converges, then the series must converge, and the second one says if the integral diverges, then the series must diverge. So in other words, the series converges if and only if the the um the integral from 1 to infinity of f of x dx converges. Okay, so that is the integral test. It gives us a way to determine if a series converges by looking at whether or not the integral converges. So a nice example. Later on, we're going to talk about the p series, which is a prime situation for that. But let's try something else. Let's look at the integral from one. Oh, not the integral. Let's look at the series. The series k equals 1 to infinity of, let's say, k squared over 1 plus k cubed to the fourth. Okay, so what is that? That's going to be the function f of x equals x squared over 1 plus x cubed to the fourth. Hopefully you can be convinced that this is eventually decreasing. I'll let you check on your own that it's decreasing when we need it. And by the way, the integral test will work if it's eventually decreasing and positive, but you want to work from, the point where you're going from. Definitely positive, everything's positive, but, well, let's just point out, 1 plus x cubed is getting bigger faster than x squared. So from 1 to infinity, 1 plus x cubed is getting bigger faster than x squared, so this is going to be decreasing. And it's definitely positive, x squared over the fourth power, and everything's positive, and x is positive, right? So it's definitely positive and decreasing and continuous on decreasing and continuous on 1 to infinity. So this is a situation where we could use the integral test. So let's go for that. Let's see what we can do with the integral test here. We're looking at the integral from 1 to infinity of x squared dx over 1 plus x cubed to the fourth. And how are we going to do this? Yeah, this is a u substitution. So if I say u is equal to 1 plus x cubed, then du equals 3x squared dx, or 1/3 du is equal to x squared dx. So this is going to be the limit as t goes to infinity of 1/3 integral from 1 to t of du over u to the fourth, right? Which is the limit. U to the fourth is just u, 1 over u to the fourth is u to the negative fourth. So we've got u to the negative fourth, which would be negative u to the negative 3 over 3, 1 to t, which is equal to the limit as t goes to infinity of 1/3 negative 1 over t cubed, 3t cubed plus 1/3. And it looks like this 1 over 3t cubed is going to 0, right? So the whole thing's going to go to 1/9, 1/3 times 1/3, which of course converges. And that really is the key thing, it converges. So this converges. And therefore, by the integral test, this also converges. Okay, so let me say a few things about what the bounds on its converging is. Okay, so I got some things out of the way and so I have something else here. We want to say something about the integral test only tells whether or not it converges, not what it converges to. However, it can be used to get an estimate on what it converges to. Now, remember, a series converges if its sequence of partial sums converge. And what I've got here, Sn, is the sequence of partial sums. And of course, you can always get an estimate for what the series converges to by taking a large enough partial sum. Question is, how good an estimate is that going to be? And the integral test is going to give us a way to bound the estimate here, so we can really see what we're talking about and get actually a better representation of S than just this a large partial sum. So let's just point out S minus Sn is going to be the remainder, kind of the error. If I used Sn as the estimate, S minus Sn is the error, what we have left, or the remainder. And what am I doing when I subtract Sn? I'm just taking off the first n terms, and I'm left with the sequence from n plus 1 to infinity. Now, over here, let's go over and look at what we've got here. This is, well, the fact that I started at 1 is sort of irrelevant, isn't it? I could have started at n plus 1 as well, or at n, right? I could have started either way. And if I had started at n here, so if I had started that at n rather than n plus 1, I would have gotten the sum k equal n plus 1 to infinity, less than or equal to the sum, to the integral from n to infinity. And if I had started at n plus 1 here, I would have gotten the sum k equal n plus 1 to infinity, less than or equal to the sum integral from n plus 1. So just using the same analysis as before, I get the following. I get S minus Sn is bigger than or equal to, so remember that's the sum n plus 1 to infinity by this bottom thing that's bigger than or equal to the integral from n plus 1 to infinity of f of x dx. And it's less than or equal to the sum, the integral from n to infinity f of x dx. And it's exactly the same reasoning as what gave us the integral test in the first place. And that gives us even a nicer way of getting S as an approximation if I add Sn to both sides. So if I take the nth partial sum, I can get S, the sum, bound between Sn plus the integral from n plus 1 to infinity and Sn plus the integral from n to infinity. And there we have it. A nice formula for getting an estimate for what the series converges to. But unfortunately, we don't have time in this video to do an example of that. So we'll stop here.